you guys. Okay, so we're gonna go ahead with the Cheryl's Law Fit Lab. So let me go ahead and play the video and then we're gonna be reviewing the questions, okay?
When an air-filled balloon at 273 degrees Kelvin is placed into liquid nitrogen at 77 degrees Kelvin, the balloon decreases 1/273rd in volume for each degree drop in temperature. Charles's law states that the volume of a quantity of gas at constant pressure varies directly with the Kelvin temperature. As the balloon warms back up to 273 degrees Kelvin, the balloon returns to its original volume.
Okay, so I know it was really quick. Now I did went ahead and put audio based on this video as well, so you're welcome to it as well. But basically, I know he went really fast, but what must be constant when using Cheryl's law calculations? Well, basically, it has to be the first of all the number of molecules. I know he didn't really say it straight out, but he did say that you have to keep the pressure constant, but also the number of molecules should be also, it has to stay the same. Okay, so that means whatever molecules you have gas cannot escape, so you must have like a really tight container to not let the gas come out. Okay, so what variables can change when using Charles' law calculations? So basically, the one that you are changing is the temperature. You're increasing the temperature or decreasing. You're adding heat, or you're taking it out. So what it is basically the temperature is basically the one that you're changing. You're manipulating it. So that will be the temperature that is changing. And also the volume depends on how you increase or how much you increase or how much you decrease the temperature. So the volume depends on the temperature. So yes, the temperature and the volume are your variables. Temperature being your independent, that's the one you manipulate, and the volume being your dependent. Is temperature and volume an inverse or direct relationship? Well, if you increase the temperature, then the volume increases. If you decrease the temperature, then the volume will decrease. So it will be a direct. That's why it's direct relationship. That means one goes up, the other one goes up. One goes down, the other one goes down. So that's direct relationship. Okay, so I'm not gonna bother with the video because I already know what's, I just go really in detail on the Fit Lab. Okay, so here I just go again very, very detailed. Okay, so in here, it's again, you can listen to the teacher audio. It's the same thing what I'm showing here. It's up to you. So click on ideal, okay, and it says, if you looked at the video, the first thing you need to do is, of course, click on ideal, and then click on particles, okay, because you want to make sure these heavy particles is highlighted in blue, not the red ones, okay. Also, you want to click on width. You want to start everything on 0. Okay, and the width is this 10.0 nanometers. So you're gonna basically add either you're gonna click this button and add 50, or you can push it up and push it down, and it should give you 50 particles. Once that turns on, then you go to pressure. And you see how the arrow goes up and down? That means the volume will be increasing, decreasing. Okay? And you see how it doesn't let nothing leave? It's a closed chamber. So your heavy particles are very constant. And the pressure needs to stay constant. But you're going to see it move up and down, but it just needs to stabilize. Okay? So the pressure stays constant. However, because we have to put the B, because the volume is the one that will be increasing, decreasing. Okay, so the first instruction says, give the pump handle one complete pump with 50 heavy particles content, which we already did. Let the pressure stabilize, which we already did. Click pressure as instructed, we already did. So increase temperature to 321 Kelvin. And then what is the volume and pressure? So we're going to increase the temperature to 321. So we're going to go ahead and add heat to it. So you see how it's like 307. We want to put all the way to 321 slowly but surely. Oh shoot. Okay, and if you go over, it's okay. I mean, anyways, it's in the video here. So let's go ahead and look at what's going on. Look at the volume. The volume is at 10.7. So it would be 10.7. So it's right here, 10.7 nanometers. That would be your volume, okay? And then your pressure, it's at 5.8 atm. Okay, so if it doesn't show that as your option, always pick the closest one. Very important. Okay, so let's go ahead and click on this as 10.7 and 5.8 atm. Okay, 5.8 atm. Okay, notice the way the volume of the container moves to maintain the same pressure. So it does move. It's trying to keep it at 5.8 all the time. What happens to the volume as the temperature increases? So now what we want to know is how this volume moves. If it's gonna get bigger, that means it will increase the volume, or will it get smaller or decrease the volume? So we're gonna increase the temperature. So what's going on? We're increasing the temperature and the volume is what? Yeah, there you go. It's increasing. So the volume, okay, what happens to the volume? The volume is increasing. If the temperature increases to 345 Kelvin, then the volume, the container will be what? So let's see if we could just lower the temperature a little bit to 345. Well, at least on my demonstration, to 345. Oops, I think I went over. Go. Oops, I still went over. It's kind of hard to keep it there. Okay, well, we'll keep it. Let's see. Okay, what is the volume? Oh, well, obviously, if you increase the temperature, then the volume will increase. If the container needs increase in volume to 12.5 nanometers, what is the temperature you need? Now, you want 12.5. So right now it's at 11.5. So as you guys can see, we cannot move the box, and we can't move this handle because we'll let all the molecules out. So we want to make sure we want to increase the volume. So obviously to increase the volume, we want to increase the temperature. So we're going to add heat to it. So until it says 12.5. So 12.5, let's see. Oh, it's almost there. It's almost there. You see how you're increasing it? That means the volume is. Okay, so what is the temperature you need? It says 378 kelvins. 378, and it's not an option, but probably because we need to lower it, but we know that it should be around there, like 375, 376. So it should be 375. What are variables associated? So we talked about this, about the variables. We're increasing the temperature, so the volume is increasing. So the variables should be volume and temperature. What is the independent variable? The one that you're manipulating. You're the one clicking on the bucket. You're adding heat. You're the one manipulating. So it was very hard. You couldn't change the box. You couldn't. Why? Because on this situation, we're manipulating. You can only have one manipulation at a time in any experiment. So since you're changing it, the temperature, that's the one that is your independent variable. The dependent, really, the volume moves according to how you move it, right? So it's the volume that is dependent on the temperature. What unit is the temperature? Well, it's a capital K, so that's your Kelvin. So that will be your Kelvin. And what two factors are held constant in Charles' law? The two factors that are always stay constant will be the number of gas particles and also the pressure. Okay, so be careful. What is the relationship between temperature and volume? Is that they have both a direct relationship. Okay, direct relationship. Okay, so again, I put another audio here, the same thing, similar to what I'm doing, but this is more visual. So if you guys see, we talked about how temperature is, temperature should be, you're the one increasing or decreasing. That's your independent variable, right? That's your independent variable. So that means that should be in that x-intercept of your graph. Okay, and then volume is your dependent variable. That means that's in your y-intercept. Okay, and of course the best answer would be this one. That's your y, and that's your x, and it's as it's you always it's as you see how the also the line how it goes up like straight line. Okay, so that's important as well. As you increase it, the volume will increase, so it should be a straight line up. Okay. Okay, so this one is D. Okay, an experiment is performed on a gas under constant pressure to study its behavior. So this is experimental data. Okay, so you have two different experiments, but this one shows if you look at the answer the following question based on the experimental data, you're looking at -10 and then increases to 12 and then 31, it increases to 51. If you look at the volume, it also is increasing. Okay, so as the temperature increases, the volume increases. So as the temperature increases, the volume increases. This is a direct relationship. Does the data of the gas behavior obey Charles' law? Of course it does. It does. Okay, now let's look at another experiment. The other experiment, and I suggest to also look at not only the graph, but look at the data as well. Okay, always look at the data as well. But again, as the temperature increases, and you see it here, then the volume will increase. You see how it is increasing? Then this one increases. Okay, when this data is graph, the result is a straight line, indicative of a direct relationship. Okay, so now let's go ahead and look at, okay, so if the temperature, let me just erase this, getting my nerves. So if the temperature of the gas molecules are 100 kelvins, what is the volume? Okay, so let's look at the temperature at 100. So if it's 100 temperature, you're gonna have to go up and then you go across. But you see how it doesn't even touch 50? It does not touch 50. So it should be, what is the volume? It should be less than 50, and it has to be what is the volume. So that means milliliters. Okay, so it cannot be kelvins. So we're gonna eliminate those. It can't be 50 because it's less than 50, and it's not halfway. You see how halfway? I mean by this halfway, like it's like right here. It's not halfway. That would be 25 because the halfway from 0 to 50 is 25 really. Okay, so it's a little bit more up there. Okay, so this one, what is the volume? It should be 40 milliliters. Okay, why? Because it can't be 50 milliliter. It can't be 25 milliliter because it's over that. So it has to be 40 milliliters. Let's look at the next one. Okay, so if the temperature of the gas molecule is 200 kelvins. Now in this one, let's look at the data graph. The data graph in here, you're going to see 200 kelvins. So we're looking at temperature, and we're looking at 200 kelvins. So that means the volume is 80. So if you look at 200, you see how it's like 80. It's close to it, but it's, that's how it resembles. Okay. So this is 80, but is it Kelvin? No, we're looking what is the volume, right? So it's 80 milliliters. Okay, now let's look at the, Okay, so the temperature of the gas are 400 kelvins. What is the volume? So if it's 400 kelvins, we know it's like in between here because this is kelvins, right? So 400 is around here, so it's between 120 and 200. So 400 kelvins, if you go up, it's not a perfect match, but you know it's going to be in between 120 and 200. So it's like close to the middle. So this one should be around, it's if it's 200, it's between, it's 400, right? So it's 120 to 200. So it could be 140, it could be 160, or it could be 190. So what's the best answer on this one? It would be, let me see, let me try to remember this one, because it's 400. So it's 400. It should be a little bit more than half or less than half. Let me see. It can't be, if it's 400 kelvins, 400. It's kind of hard to tell with the graph, but it would be, this one is should be 160. Okay, because it's like the closest one would be closest to half. You see that, how it's let me see, because it's 400, so 120 to 200, so half of that will be 160 milliliters. Okay, if the volume of a gas molecule is 20 milliliters, what is the temperature? So the volume of a gas molecule is 20 milliliters. Now we're looking at it backwards. But, you know, we could always use the data table. So if it's 20 milliliters, that means it is 50 kelvins. Or you can always look here. 20 milliliters is around here. So it's a tougher one around here. But you know that it should be around half of that. So it's 50 kelvins. Okay. If the volume of a gas molecule is 55 milliliters, what is the temperature? So that one should be around, if it's 55, you know, it should be right before 150. So your best option would be right before 150. It would be 138 kelvins. And that's a wrap, you guys.